Now, how can I write this probability? Okay, so I can write this probability using, what do you call, how the probabilities can be computed actually, something that is about the random variable x and y. Such probabilities can be computed by integrating, okay, integrating what do you call the PDF of x and y, okay, with respect to dx and say with respect to y, dt over the region where this constraint is satisfied. Where this constraint is satisfied, okay, over the region. So like you are computing this integral on all points such that g of xy is bigger than t. So this is the set actually on which you are doing the integral. Okay, maybe I can write it explicitly that okay, if I call this region R, integrating over the region R, then the region R is the collection of the ordered pairs such that g of xy is bigger than t. This is what is going to be the case actually. If you, so this is dx dy over the region R. Okay. So now if you change the order of integration actually, okay, if you change the order of integration, in other words, you take these dx dy outside and bring this dt inside, okay. So if I flip, if I keep dt here and dx dy outside, then what will happen actually? Then this will happen, that you will have the integral, okay, over some domain of x and some domain of y, and the integral of say fxy of xy dt and dx dy. Now what is the variation on t? What is the limit on the t actually? So the t is a positive number. That should be a positive number actually, because you know gxy is bigger than t, okay, and its gxy is non-negative. So the t is going to stay between 0 and up to gxy, okay, gxy. So this is what that you're gonna get. Okay, so maybe let me write this as g of xy. So change in the order of integration would give you this. And what will happen next actually? Okay. By the way, on okay. By the way, then what will happen actually? Then the final thing that will happen is that now the integrand of this inner integral does not depend on t. So you can pull this f of xy out of integral actually. So if you're gonna have this, what are you gonna get? You're gonna get a double integral of fxy of xy, and what is going to remain inside is 1, and if you integrate 1 you're gonna get t, and in that t if you substitute the limit you're gonna get g of xy minus 0 actually, and I can ignore the 0 anyway. You have the dx and dy. Okay, you have the dx and dy. So you got what you call almost the same result actually. Okay, so almost the same result. So my point is this. So this is just in a sketch. I mean, we can make it more rigorous, but okay, this is just a simple sketch actually. And I mean, if you see, its proof is very much analog to what you did in the one dimension actually. Its proof is very much analog to, you know, what do you call, what you did in the one dimension. So what does this simply means? That if you want to find the expectation of function of x square plus xy, what you're going to need, just integrate it or sum that function, multiply with the PDF and integrate actually. For example, if your g of xy is say x square plus y cube, and you want to compute say expectation of x square plus y cube, this would be what? So this would be, what do you call, the double integral, okay, from minus infinity to infinity, from minus infinity to infinity of x square plus y cube multiplied by the joint PDF fxy and then integration dx dy. Okay. So this result allow you to take any nice function for which the integral makes sense, okay, and compute its expectation actually. Compute its expectation. Let me do one example based on it. An interesting practical example. So this is just a straight generalization of the two, and you can even generalize this result in 3 dimensions as well actually, 3 and higher dimension. That instead of g of xy, you have g of xyz. Then everything would be same. You're going to have only a triple integral, and g of xyz multiplied by the joint of f of xyz, and just solve that volume integral, and you're going to get your result actually. So here's an interesting case actually. Imagine you have a road that has a length L, so the length of this road is L. Okay, we call it a road actually. Okay. And you assume it a motorway or something like that. Okay, and assume that on this point, on this road, there is a chance actually that an accident can occur at any point actually. So in other words, at any point on this road that has length L, an accident can occur actually. Okay, so I'm saying that x is, say for example, point on the road, location on the road where accident occurs actually. Okay, accident may occur. Okay, then what should be the distribution of x actually? So it's a really ideal kind of a situation. So you're going to say, so the x can ideally have, for example, a uniform distribution over the interval 0 to L actually. So starting from 0 and ending at, say for example, L. Okay, so in other words, the location where an accident can occur is any point between 0 to L. Okay. Now, at the time of accident, okay, at the time of the accident, so imagine that accident occurs uniformly, so at a random point on this road. So let's call this point A, X, and let's assume that there is an ambulance actually at a uniform point. So on this road there is an ambulance which is kind of going back and forth actually to track that where accident might have occurred, and so that you can help them actually. So if accident occurs at a random location, on this road at this point, and imagine that Y is the location where there is an ambulance actually. Okay, Y is the location where there you have an ambulance actually. So the Y is the location, okay, on road where you have where the ambulance is actually. Okay, is ambulances. So in other words, they can be near to each other, they can be very far to each other. So ambulance can be here, and accident can be here, and so on and so forth actually. And so the Y, we are assuming that Y has also a uniform distribution. In other words, y can be uniformly at any point, the ambulance can be uniformly at any point on this road actually. So let's assume that y has can also be, so it has a uniform distribution over the interval 0 to L actually. Okay. Now let's assume, and we should assume actually, that x, the location where the accident has occurred, and y, the location where the ambulance is there actually, are independent of each other actually. Okay? Are independent of each other. If they are independent of each other, what would be their joint PDF? So fx of xy is going to be what? In other words, fx of xy means what is the probability that x is at a location x, on the road, okay, and y is at a location y on the road. Say for example, you call this as a 0 point, a starting point, and you call this as an ending point, say L. Or you can flip it, okay, otherwise, as well actually. Now since x and y are independent of each other, so you can write this as fx of x times fy of y actually. Okay, fx of x and fy of y. So what would be the joint PDF of it? So the PDF of x, since it is uniformly distributed, is really 1 over the length of the interval, which is L, times 1 over L, where x is between, or maybe I can directly write 1 over L square, okay, where x is anywhere between 0 to L and y is also anywhere between 0 to L and equal to 0 otherwise. So this is what is really the joint PDF. Now, what is the key question that we will like to find? What should be, so we haven't said, what should be the average distance between, or what must be the average distance between the location at which accident has occurred and location where the ambulance is, and obviously the ambulance is going to move towards rescuing the people who have kind of suffered through the injuries actually. So so in other words, what should be on a road of length L on average, what should be or what must be the expected distance between both actually? So this is going to be an interesting question. So what should be the expected distance between both? So say x is at a location, so the accident has occurred at a location x, and ambulance is at y. So the x minus y is the distance between x, the location where the accident occurs, and the location where the ambulance is actually. Okay. But it's not necessary that x should be here and y should be here. So the y has a less length and x has a more length actually. Okay. So you could have a case that y is here and x is here actually. So it's better to put an absolute actually. Okay. And the question is, what would be the expected distance between these two places actually? Okay. So I want to compute the expectation of absolute of x minus y. Now, this is same as that you apply your previous formula for the function g of xy, where the g of xy is absolute of x minus y. Okay, so how can I compute this integral? So for computing this integral, I'm going to say that, okay, let's integrate the g of xy, which is expectation of x minus y, times the PDF, which is 1 over L square, but this PDF is in this rectangle actually, so it's in 0 to L and 0 to L actually. Otherwise it's 0, so it will not contribute anything into the what you call function, and then integrate over with respect to x and with respect to what you call y. Okay. I'm not solving this integral for you. You may solve it yourself. It's not a difficult thing to solve. So obviously, what you can do is that, okay, you break this down, this integral into the two parts. That the absolute of x minus y is going to be x minus y if x is bigger than or equal to y, and it's going to be negative x minus y, okay, when y is less than or equal to maybe x is strictly less than y actually. Okay, so this is what is going to be the case, and then, you know, using this definition of absolute, try to compute this integral. When you will compute this integral, okay, I'm just directly writing the result, you will get a very interesting answer, and that answer is going to be L over 3 actually. L over 3. Okay. So the expected distance between, and you can see that this could be an example of, you know, very interesting importance actually. So for example, you know, you have this motorway, say for example between Karachi and Hyderabad. You know, it's a long motorway, you know, and you know the cars go really fast. Okay, and you know, quite often, you know, accident occurs actually. Okay, now if we assume that there are, for example, some patrolling car, you know, the traffic police car, motorway police car, which are not located at a certain location actually, they just move back and forth on the road actually. Okay, so if you have say if accident has occurred at a location, for example on this Hyderabad Karachi motorway, God forbid, then the expected distance between the motorway police car and, you know, the rescue car and the location is on average going to be the length divided by the 3. And say for example, I think this Karachi Hyderabad motorway is around, you know, 120 kilometer actually. So in other words, around, you know, most of the time, if we assume that, you know, their locations are uniformly distributed, you know, the average distance between the location of the accident and the the police car or the ambulance is going to be, you know, 120 divided by 3 means 40 kilometer actually, most of the time. So that's a very interesting conclusion that we can get through what do you call these concrete numbers. Okay. All right. What are some more properties? Some more properties. So, for example, another property, and I think I gave this you in exam. Actually, I'm not going to prove it. I talked about it in a Zoom session as well. That if I have a random variable x that is bigger than or equal to y, then the average of x should also be bigger than or equal to what you call y actually, average of the y. Okay, expectation of x should be bigger than or equal to. So one of the way could be that since since say x minus y is bigger than or equal to 0, so this means this. So the expectation, so in other words, the values that x minus y takes should also be bigger than or equal to 0. Okay, and if you, for example, multiply it with say the joint PDF of x, y, and then integrate, then this integral should also be what do you call non-negative. In other words, that the expectation of x minus y should also be bigger than or equal to 0. And then we know about that the expectation, if you have expectation of two random variables, then the expectation of two random variables can be seen as the expectation of sum of random variables or difference of random variables is equal to the expectation of the expectation of the sum is the sum of the expectation, or the expectation of difference is the difference of expectation actually, and this really proves the identity actually. So if x is bigger than or equal to y, then average is also going to be bigger. I mean, if you remember that we showed in our previous chapter that if you have two random variables x plus y, then their expectation can be written as the sum of the expectations actually. Okay? So maybe one exercise for you to generalize this for n random variables actually. By the way, I think we also proved it, that if you have expectation of what do you call the sum, at least in the discrete case we proved it, then this should be same as the sum of the expectations. Okay? You can prove it inductively as well. So you can run an inductive argument and you can say that the expectation of the sum of the random variables is equal to the sum of the expectations actually. Now what we are going to do, we are going to take different kind of n random variables and we will try to compute their expectations actually. In other words, that I know that this identity is true in general. Now if I assume some distribution for x1, x2 and up to xn, okay, x1, x2 up to xn, then you know what would be the expectation of the sum actually in different cases. Okay? What would be the sum of expectations in different cases? So for example, let's start with say sample mean. Sample mean. So imagine I have some x1, x2 and xn are some random variables. They are IIDs actually. Okay, so we'll define IID. IID means they are identically distributed, identically or maybe independent and identically distributed. Independent and identically distributed. Distributed actually. So imagine you have n random variables that are independent of each other and they are identically distributed. And by identical distribution you can also mean that they have the same kind of distribution actually. So either all are binomial, either all are normal, either all are Poisson and so on, with the same mean and same variance actually. Okay, so with the same mean for example. Okay, so IID with same mean, with the same mean. That is, that if you compute the expectation of every xi, then the expectation of xi is going to be say a number mu actually for any I 1, 2, 3 and up to n. Okay. Now consider the sample mean. So what do you mean by sample mean? The sample mean of this is going to be simply sum them up, I equal to 1 to n, okay, and divide by n actually. The question is, what is the average of this sample mean? Okay, what is the average of this sample mean? So you can compute it by applying expectation, for example, on both sides. 1 over n is like a number, you can pull it out. Okay, 1 over n is like a number, you can pull it out. So we have this property of expectation actually, that expectation of a constant multiplied by a random variable is a times of the constant multiplied by the expectation of x. So 1 over n I can pull it out. And then the expectation of sum is the sum of expectations. So we saw it actually. And we proved it as well in the previous set of discussions. So it's going to be sum that goes from I equal to 1 to n expectation of xi. Now, since we have assumed that they all have the same distribution and they are identical, and the expectation of xi is mu, that means that this number is going to be the sum of the mu I equal to 1 to n and everything divided by n. So it's like you are summing one same number n times. So this should be equal to n mu over, for example, n. So our outcome is mu. So in other words, the mean of the average of the sample mean is the same average actually that each one of these random variables have. Okay, so nothing is really changing based on it. Say, you can take different kind of, another interesting, for example, application of, say, this identity is that, that you can prove the Boole's inequality with this actually. And if you remember, what was the Boole's inequality for the finite union? That imagine you have n I equal to 1 to n ai and events, and you want to compute the probability of union of ai. This probability can be estimated or should be estimated by the sum I equal to 1 to n probabilities of each one of ai's actually. Okay, so this is the probability of the union of ai's must be less than or equal to the sum of the probabilities of ai's actually. And I mean, if you remember, you proved it in a different manner using the properties of the probability measure in your exercises, but you can also prove this using this expectation actually. Okay. In order to prove this identity using the expectations, what I would like to define is so corresponding to each a1, a2, an, let me define some n random variables x1, x2, xn. Okay, for ai, let's define xi. Well, the xi is really the indicator function of ai actually. So the indicator function of ai. Whether we know that the indicator function of ai operated, for example, onto an x would be equal to 1, or I can say that this would be equal to 1 if ai occurs. Okay, ai occurs, and it should be 0, if ai does not occur, okay, otherwise, or ai complement occurs actually, okay, or you can say otherwise. Now, let's denote the x. Let's denote the x as the sum of these xi's, I equal to 1 to n xi. Okay? So x can be interpreted as what? So the x can be interpreted as the number of events that occur. Number of events ai that occur. What values